All right, hello everybody. Today we are going to be covering Dalton's law and Graham's law. So these are the last two laws and equations that we need to worry about. Tomorrow we're going to start getting into a little bit more of states of matter and the different types and that kind of stuff. So also make sure you turn in your worksheet from yesterday, have all your work shown, and let's get into it. So recall that gas pressure results from collision of particles. So what's happening is all these particles are bumping and colliding with each other and with the sides of the container, and that's what's creating this pressure. So gas particles depend on the amount of gas and kinetic energy of the particles. So again, how much is in there? Because again, the more that's in there, the more collisions that's going to occur, the more pressure. And also same with the amount of energy or kinetic energy it has. The faster they're moving, the more collisions that can occur. Since particles in a mixture of gases at the same temperature contain the same average kinetic energy, the kind of particle is unimportant. So we don't care if it's a nitrogen atom, a hydrogen atom, a chlorine atom, it doesn't matter. The main thing is, as long as the temperature is consistent and the kinetic energy is about the same, it's going to be the same regardless. So for example, let's look at the composite of dry air. So this is air without water in it. So nitrogen is about 78% of the volume at 79.11 kPa, which is their partial pressure. Oxygen is about 20%, almost 21%, which would be a partial pressure of 21.22 kPa. Carbon dioxide, so again, carbon and two oxygens together, is 0.04%, so that's 0.04 kPa. And then other miscellaneous gases, whether that is going to be bromine or fluorine or whatever other gas we're dealing with, hydrogen, that's 0.93%, and so your partial pressure would be 0.95%. When you add those all together, it'll give you about a 101.32 partial pressure for the total mixture of air. So that's why when we say there's 1 atmosphere, it's also equals to 101.3 kPa because of the total amount that we have. So our equation, or Dalton came up with this law, it says the total pressure of a mixture of gases is equal to the sum of its individual partial pressure. So basically saying the total pressure is adding up all of these partial pressures together. So here's Dalton's law of partial pressure. So P total equals P1 plus P2 plus P3, and it just keeps going. Now the major thing with this is that their units have to match. If their units don't match, you need to convert them to their units actually matching. So let's do an example. So what is the total pressure for a mixture of oxygen and carbon dioxide if pressure oxygen, so pressure O2 is where that's coming from, is 0.719 atm, and the pressure carbon dioxide is going to be 423 millimeters of mercury. Okay, so we're looking at these and they don't match. So our oxygen's pressure is in atm, our carbon dioxide's pressure is in millimeters of mercury, so we need to convert them to match. It doesn't matter which one you convert to, I will always make sure to have the answers for both. I'm just going to convert mine, let's just do it differently than we normally do. Let's convert our atm into millimeters of mercury. So I'm going to build my train track out. So I know for every 1 atm, there is 760 millimeters of mercury. And so what we're going to do, we are then going to multiply, then divide. So 0.719 times 760, you should get an answer of 546.44 millimeters of mercury. Okay, so now what we're going to do is we're going to take those two pressures and add them together. So 546.44 plus 423. And when you do that, you should get an answer of 969.44. Now again, got to put it into sig figs. So look at my first number. This is 3 sig figs. The next one's 3 sig figs. So I'm going to put it into 3. 1, 2, 3. Look behind, it's a 4. So we're going to stay the same. So that'd be 969. And again, we converted both of them into millimeters of mercury. So our final answer will be in millimeters of mercury. So that's as easy as it gets. Make sure your units match, add them together, you're done. That's all you gotta do. So Dalton's law, very, 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 very easy. Oops. Okay, now we're gonna get to our very last law, which is dealing with Thomas Grant, or Graham. So we call this Graham's law. So with Graham's law, we talk about the difference between diffusion and effusion, because Graham's law sticks to effusion, but it does sound very similar to diffusion. So diffusion is the tendency of gas particles to spontaneously spread out until uniformly distributed. So when you have a diffuser at home, or you have an open container of a gas that smells and it spreads throughout the room, that is diffusion. Effusion is the escape of a gas through a tiny pinhole of a container. So gases with a lower molar mass effuse more quickly. This, I would star, highlight, whatever you need to do, because that's the most important part of Graham's law, is that whatever one has the lower molar mass is going to effuse faster. So effusion is basically when you have a mixture of gases in a container and there's a pinhole, and it allows you to separate your two gases. So generally the smaller molar mass, or the smaller mass, is going to be able to fit through that hole a lot easier, and so we can effuse those gases out and separate them from the other gases that are larger. On the slides there are 2 videos you can watch talking about the difference between diffusion and effusion, so just so that if you want to go watch it, great, but these kind of both explain the difference between them. So, Graham's law, the rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. So you will have to be able to solve for square root. Good thing you get to use a calculator that has a square root function on it. And we solve for molar mass. So here is Graham's law. Oops. So rate A over rate B equals the molar mass of B over the molar mass of A. The main thing, again, star, highlight, whatever you got to do, the bigger molar mass is always going to be on top, regardless, every single time. So always place the larger molar mass as the numerator. Again, numerator is the top of a fraction, so that you're always going to get a positive integer. Otherwise, if you do the other way, it won't work out correctly. So bigger number on top, smaller number on the bottom when you're solving for molar mass. So let's do an example. Which gas effuses faster, hydrogen or chlorine, and by how much faster? Okay, so we said our equation is rate of A over the rate of B. And again, we're trying to figure out which one's going to go where. Equals the square root of the molar mass of B over the square root of molar mass of A. Okay, so if I look at these 2 molar masses, well, chlorine is 35.45 for 1 chlorine atom, so that would be 70.90. So that would be 70.90 for the molar mass of chlorine 2. Hydrogen is 1.01 times 2, which is 2.02 equals the molar mass of hydrogen. So since chlorine is bigger, that means we're going to have our rate of chlorine with our rate of hydrogen on top. So when we solve, we're going to have the chlorine, our 70.90, over the square root of 2.02. So again, these are flipped. So this is chlorines and this is hydrogens, so that you can cross multiply. So what I would do here, I would take my 70.90, square root that. You should get 84.202137774 over, take 2.02, square root that. You should get 1.42167704. We are going to then divide those 2 numbers. And you should get an answer that equals 5.92. And it might be like 5.9227, whatever. I would say go to 3 sig figs. Not going to be super strict on the sig figs for this one because there's no numbers for you to pull from. So you should get an answer of 5.92. So that would be 5.92 times faster. So again, hydrogen is the smallest, so that means it's going to effuse faster. So hydrogen gas will effuse 5.92 times faster than chlorine. And that would be your final answer. So the major things with these problems, one, we know how to solve for molar mass now. We should be able to do that in our sleep, no problem. I would solve for square root of both of these first, write those answers down, and then divide. It just makes your life a lot easier when you're solving through these problems. Also, the smaller molar mass is going to effuse faster. So if you need to leave yourself a note and say, this is going to be effused faster, or you could say, well, let's just write faster or fastest effusion, so you don't forget something. Because a lot of times that's what gets students is we forget which one is supposed to be the faster or slower one. You could also just circle it and say, okay, this is the one that's going to effuse the fastest because it has the lowest molar mass. All right, so that's all I got for you today. Pretty short and sweet, nothing too crazy that I don't think you can handle on your own. So make sure you grab your Dalton and Graham worksheet. That'll be due tomorrow when you walk in. We'll go over it. We'll also go over the ideal gas law worksheet from yesterday, and then we'll get into states of matter. Please let me know if you have any questions, and have a great rest of your day. See